Welcome to the very first class of your Applied AI. This semester, Marco and I will share, but instead of Marco teaching one section or one class, I teach another class. We're going to switch. So, for example, this week I'll be giving the introductory lecture, and then next week Marco will come in. So we'll kind of like switch the presentation a bit. Right. So let's first understand what we're trying to do. Today's lecture, I call it AI in Context. It's a bit of a historical introduction of how we got here and where we go from here. Right. But first I want to give you a perspective on what the class is or should be all about. Okay. Now, AI as a piece of technology, we'll go into in-depth detail of where you place in it, is one of those things where now that it's getting all the currency and all the hoopla and so forth, right? Everybody wants to apply and see if they can use it in their lives or in their business. And this class is, well, it's exactly about that. It's about applying AI. So, first of all, it's not about the core technology itself. Okay? It's about applying it. Having said that, consistent with Basai philosophy of education, we are not a plug-and-play kind of student, right? Where you take a black box from here and, sort of like, here's a car, start up and go. Okay? So you're not just a pure driver, you're not just learning how to drive a car, but you actually know how mechanically, at least in principle, okay, in principle, how does the car work? So when something goes wrong and when you want, when you want to soup up your car performance, you actually know how to address. So you know different sort of like in principle how things work under the hood. Okay? And so this class is going to try to strike a good balance between giving you an understanding of how things work under the hood, as well as how you can practically play with it or apply it, right? Now, you may not be convinced, I hope you are by now, since you're a third-year student, that knowing how the technology works under the hood is not just a nice-to-know thing. Right? It's like one of those, I don't know if you watch a Formula One car, but one of the keys of Formula One racing, but one of the key success of Formula One driver is one who actually understands or sympathize with how the car works, because he has to actually feedback with the engineers. Okay? So if somebody who is just good at playing video games and can withstand a lot of G-loads, yes, you can put this guy in a Formula One car and he can drive pretty fast, but he definitely can't get faster because he doesn't know how to interact with his engineer, his race engineer, to set up the brake bias, to set up the sort of like the engine parameter, suspension parameter, and whatnot. Okay? So it's a little bit like that. It's a little bit like that. Okay? I myself will lean on the understanding side, okay, whereas I would leave it up to Marco and the wealth of his experience to embellish you guys with the actual, how to, okay? But you learn a lot, you learn theoretical foundation from him as well. Right. Okay, so that's it. That's the first slide now. Okay, this is where we are. We are Chulalongkorn School of Integrated Innovation, Basai. Since I haven't met with a lot of you, maybe I'll take a minute or two just to make sure we're on the same page, right? When we say integrated innovation, we don't mean we put good idea here and good idea there and put them together in an app. That's not what integrated innovation is, right? I often joke that if you like to play with your cat and you like to drink coffee, and you're having a platform that tells you when the cat is ready to play and when your coffee is ready in one place, that's not an innovation. That comes from integration. Integrated innovation means you yourself have integrated multidisciplinary education, art, science, technology, biology, physics, chemistry, linguistics, okay? And then you are the integrated package. And it's that kind of integrated education that creates a human resource, namely the inventor, that really makes meaningful innovation. Okay? And that's and the art of science means that we are following the sort of like liberal arts tradition, where there's no separation, there's no big Chinese wall between what's art, what's science, what's creativity, what's engineering. Everything is fused, hopefully, in your brain. Okay. Oops. I'll just use page down, maybe. Page down, page up. Okay. This is a little bit about me, but it's not important. By the way, I've always said, and some of you may have been in my class, in my career, I must have written 10,000 PowerPoints in my life, PowerPoint pages. As much as I can, I would not use PowerPoint for my student, because it's too linear, I think. Okay? PowerPoint is very good when I go on consulting pitch, because I start with a page and say, you've got a problem is really big, there's actually technological solution, people are offering the solution, and the final page of the PowerPoint is, hire me as your consultant because I'm the guy for you. So PowerPoint is it's not manipulative by intention, but it's that kind of tool. It linearizes your journey from the beginning to end, from slide 1 to the last slide. Okay? So I try as much as I can not to use PowerPoint, and the student usually asks me, is there a PowerPoint for the class? I never provide that. Okay? Even though I myself write them professionally. Now, in this case, I'll make an exception, because this is kind of like slides that occasionally, many times I've been asked to give a public talk on the technology, right? Where AI is, how it fits in banking and finance. So I do have a PowerPoint ready, and I think, I'm just being lazy here, to be honest. I kind of adapt from that. Okay? Anyway, so got my obligatory background. You don't need to know anything except the fact that I am also a product of your philosophy of education, even though, your program only started 3 or 4 years ago. My undergraduate is in what's called a liberal arts school, which means it fuses arts and science, and you don't go to a department. Okay, you don't get admitted to a department, you get admitted to the university as an undergraduate. And you can take any subject you like from across the campus, right? And you create a concentration, they call it major. Maybe you have a minor, okay? My interest was kind of diverse, so I took a double major in physics and economics, okay? Physics is a long-time passion of mine, and it's a lot of fun. Economics, just by chance, that one day I was looking through an old in the United States, in many Western countries, they share it old books. So they have this kind of like a flea market for old books. I just picked up an old introductory economics 101 book, and maybe the author wrote an introduction that was very convincing. So I kind of took economics. So anyway, so that's what the only thing you need to know about me is that I too am a product of liberal arts education, fusing art, science, technology, engineering, and so forth. Now, I went on to do my master in operations research, which in itself is a multidisciplinary field. Okay, some of you that take applied digital intelligence track maybe would understand that. It's a lot about applied math. Then my Ph.D. was in computational intelligence, what back then was the umbrella that covers AI, decision-making optimization inspired by nature. Some of you may have a friend who study things like swarm optimization. That's kind of a newer version of some of the things I've studied. Anyway, so the idea is that hopefully I sympathize and bring the best out of your multidisciplinary education. Now with BASI, it's a little different. So you're not taking classes from all over Chulalongkorn University, but we try to sort of like take bits and pieces from the frontier of knowledge and pre-synthesize them for you, so to speak. Okay? So, right. So enough of that. Okay. Again, this is a legacy from professional slide. I use this slide just to say that you guys know what a hockey stick graph is, right? There's a plot that's say global temperature, right? That's sort of like been, since humanity became civilization, agrarian civilization 2,000, 3,000, 4,000, 8,000 years ago. The Earth temperature is kind of like hovering, in some baseline level, and it kind of shot up like a hockey stick during the Industrial Revolution, right? Now that temperature coincides also with the carbon dioxide, not coincide, coincide is a good word. Coincide with the carbon dioxide part per million. As recorded, for example, in ice core. When you go to Antarctica, scientists drill ice core down. They can actually have sampling of the atmosphere going down thousands of years. Okay, so there's a spike in carbon dioxide that actually happens this sharp turn. Okay, so they call it hockey stick. Well, the thing is that hockey stick is happening vis-a-vis technology as well. In particular, you are at the inflection of the AI technology, right? And today, I'll give you a little bit today is all about background. You actually see how the technology, how we got here today, and how we are actually taking this sharp rise, this kind of inflection point, okay? Okay. Now this is happening in all kinds of things, right? It's happened with genomic science. This inflection point hasn't quite arrived vis-a-vis, say, quantum computing yet, but I'm sure in your lifetime it'll be the same story. Okay? So your generation is sort of like a little bit unique. Okay? Every generation is unique in its own way. Yours is the confluence of inflection points. Just remember that. Okay? Could be good and bad. Technologically, it's good, but environmentally, not so good. Okay? But that's your generation. You're going to experience that in your lifetime. It's a confluence of inflection point in the history of mankind. Okay. Subject of today, AI in context. Techno-historical introduction, how did we get here, and where do we go from here? Okay, this is sort of like a rough lay of the land outline that I tend to use at the beginning of my introductory talk about where the set of technologies are, but we will be more in depth about this. But the idea is that we have these four things. Oops, there's this thing that's kind of blocking. Let me see if I can move that. And that down here. Well, it's going to block no matter what. I don't know if we can make this vertical, but anyway. There are sort of like four bits of technology that are swirling about. One is AI, one is machine learning, one is quantitative models, all kind of things. You may have heard of quant finance, or this guy paid a lot of money because he's a quant. That's what quantitative models are all about. And data analytics, which is actually a selective class I teach at BASI here, right? Some of your colleagues. And these are kind of like thrown together as new set of technology that corporate world has to wake up to. Okay? And the story tends to be something like, we have a lot of data, big data, can we apply AI to it? And we hear this thing about machine learning, and in our bank we have a team of quant. I don't know what they do some kind of derivative pricing, but what else can they do with data? So this is sort of like to set the orientation, okay? The story, and I'll flesh it out in the bulk of the lecture, is that according to my perspective at least, the story should start with AI, funny enough. Even though AI is like the new tool, to me, story starts with AI. AI, in this case, and we'll talk in detail, it's about aspiration to see if we can model intelligence, human intelligence in an artificial way. So this is kind of like fresh after World War II in the 1950s, okay? So, that's it. Has nothing to do with application, okay? There's no such thing as applied AI, right? It was pure intellectual. And you see a lot of this, by the way, in every subject you study at Basai. It usually starts out from curiosity, right? It never starts out with, hey, let's make an app, or let's become an entrepreneur and make a lot of money doing this and sell this, and this is a business pain point. No, it usually starts out as curiosity. In this case, the curiosity was, how can we get artificial machine, i.e. computer, to behave like human, okay? The idea is that, well, computer has to be programmed. Computer has to be programmed, right? In fact, a lot of you are learning about coding. Well, it turns out that they tried to program intelligence into computer. It didn't work. It didn't work. So instead of programming content or intelligence into a computer, they kind of go backward and say, how about programming the computer an algorithm so that it can learn by itself, so to speak. So it's not programming a computer with the content, but it's programming computer with algorithms so that it can acquire content, so to speak. So that kind of like gave birth to what's called machine learning. Okay? So AI actually motivates machine learning. Now, since then, there have been a myriad of machine learning algorithms that has absolutely nothing to do with AI inspiration or aspiration. It's a machine learning that sort of like teach a computer how to learn how to do this and that. Nothing to do with AI. So it became like a huge field on its own. So machine learning is, in a sense, it's not a subset of AI. Maybe in the beginning it was, but not anymore. It's a huge area, okay? And well, now that you have machine learning, it builds capacity of computer algorithm to do all kind of functions, all kind of apply math. So basically, whereas you used to have to program mathematical function to do things, now you can let computer build mathematical function. So machine learning now builds like a catalog, huge catalog of quantitative models. Okay? So it kind of builds quantitative models. Now, once you have quantitative models, okay, you have to calibrate it with data, right? And now there's a virtuous cycle where you build a model, you feed it data. The model is as good as as the data you give it to, garbage in, garbage out, you've heard of that, right? So you have a quantitative model, like a regression equation, it's only as good as the data you give it. So over time, it becomes a virtuous cycle where, well, you realize you need good data, good model, so people became more conscientious about keeping data, right? And of course, we digitize all kind of data, so now data just blow up to, some of you may have heard the term big data. So now, you're trying to gain business advantage, competitive advantage by analyzing the data you've got. So data analytics became its own giant, okay? And that giant is basically driven by quantitative models. Okay? If you have a whole bunch of data in the database and you don't have any model, it's useless. Yeah? So it comes back full circle where data analytics, okay, or data itself validates the whole concept of AI. Okay. Now, when I create this slide is very old, by the way. Okay. Came long before ChatGPT. So the word validate in the sense is sort of like validating how we got to AI in the first place. But now you see that AI itself, because it has this capability, now I'm sort of like jumping to the end here, AI has generative capabilities. Well, once you have generative capability, it's like teaching a 4-year-old to speak. Pretty soon he's going to start saying all kinds of stuff, sense and nonsensical. So now you have this data that's sort of like rein in the ground truth. So it actually validates it in even more precise sense, mechanical sense, that yes, you build a model that's AI, but now instead of validating by how well it looks like a human being, no, you validate it by how well it gives you the truth, or how well it links to reality of physics, of economics, of current events. Okay? And so data now comes back and validates this whole concept of what it means to be intelligent artificially. It's a gorgeous story of good karma. What goes around comes around. And this takes place over, let's say, 3/4 of a century. Okay, I would say the end of World War II to today. Okay, this big giant loop that I'm telling you about. So, it's down. Okay. Now, let's start getting into the nitty-gritty. Okay? And I tend to do this a lot because when there's a term running around, we should break them up. Okay? Break them up, break them down, and sort of like put individual component under the little microscope. Okay. Oops. Blocking this thing again. That's a good place for it. First of all, the I in AI. Now, I could be a little bit more fancy with my presentation, sort of like hiding some points and just sort of like revealing them as they go, but I couldn't be bothered. Well, actually, there are 3 meanings that you don't realize, and I want you to realize, and that's sort of like a take home. You must, you can't consider yourself having gone through this class or maybe passing a midterm unless you know this. Well, the first meaning of intelligence in AI was, the original meaning was human-like, because we consider ourselves intelligent mammals, or the most intelligent species on Earth. Okay? And we measure intelligence in our human-centric way. Okay? So yes, you can say that in many objective sense, we are superior in our intelligence, but it's also relative, because we are intelligent in every which way, but finding nectar or finding water in a desert land is not an intelligence that we can outperform lizards, for example. Okay? But the idea here is this. We define ourselves as intelligent. So the intelligent and artificial intelligence means, how can we artificially create resemblance of human being? Not resemblance of intelligence, resemblance of human being. Okay? And that basically that basically is the very meaning. Now, the character I will show you, and we actually will watch videos toward the end, of Alan Turing. You may hear of the movie called Imitation Game, right? Well, that movie has nothing to do with the imitation game. What it has to do with is Alan Turing, who then created the imitation game. But the imitation game played no role in that movie. Okay, that movie took place in the World War II. But the imitation game is, can we get a computer to imitate human being? Now, back then, computer didn't have this interface that you guys have. So it's basically you have to sort of like key in with paper code or something like that. I remember growing up, my father was one of the very first person in Thailand who actually brought in computer technology, or sort of like utilized. And back then we used what's called punch card. This is really, I wish, I don't know if we still have it in my mom's house, but it would be like valuable today. It's basically a deck of cards about this big. It's a card about this big. Each card has all the characters, and you do a little bit of punch hole. Okay? And when you feed that into a machine, it reads an instruction. So actually feed a stack of paper. Anyway, and that is even newer technology than when Alan Turing was conceiving imitation game. Okay? So, the imitation game, right. So the imitation game was, well, you can't have Android interface like we have today. So what we do is we lock the computer in a room, and you have a human being, and you converse with it, but you can't do it verbally or using audio because technology didn't exist. So you write English words and feed it to that room, and then that room, turn this to computer, feed input the computer, and the computer would give back response. Write it out, maybe in human handwriting, and push it through the door again. And the idea is, you ask that human being, okay, does it feel like you're having a conversation with another person in the other room? Okay? Are you convinced? Is it convincing enough that you think that you're actually talking with another person, who's mute or something, who can't speak, who can't hear, but can write? Okay? So if you can carry on a good conversation, it's considered 100% perfect AI. Now, does it matter that the output or the response you get is completely stupid? It doesn't, right? You can say, hello, how are you today? And the response is, fine, thank you. What's 2 plus 2? Well, that's 4, obviously. And what's 3 factorial? I don't know. I only, in grade school, we don't know what factorial is. Or, what's better, education or computer game? And say, oh, computer game is much better because it's a lot of fun, or something like that. So completely silly answer. But as long as it seems like a human being, it's considered intelligent in that definition. Okay? Good enough. The modern incarnation, by the way, this was a challenge that was very difficult. And now we take it for granted in the form of chatbot, right? Okay? So, if you go to online shopping and then you have query and you ask for customer support, and the customer support respond back to you, how can I help you today? Please let me know. Okay, is that all you need? Can I suggest another product? That sort of thing, right? It sounds very human. That's good enough. Okay? Now because we know the technology, we assume it's actually a bot, not a human being. Okay? But if you didn't know this, you would have been fooled as well. Okay? The answer can be stupid, even selfish. Like whatever answer you ask, it's going to say, buy this, buy that. Okay? Even though the intelligent thing is to say, oh, save your money, don't bother, this product is not good. Okay? So the quality of answer has nothing to do with intelligence. Intelligence is about human life. That's it. That's all you need. And like I said, the legacy or the accomplishment of that today is a chatbot. So I would say that maybe 4 or 5 years ago, when Basai started, this is before large language model blew up. If we were to teach applied AI course, honestly, it was about how to build a chatbot into your app. It would have been about that, very narrow sense, right? You have an innovation, but then you want to have an interface with your client, but you don't want to hire somebody to respond to tweet or inquiry. So let's see if we can build a chatbot or something like that. That would have been the bulk of applied AI. Okay. Fortunately, you're even more fortunate, and this is the deal. You are actually getting revised curriculum by nature every single year, every single term. So next year, your younger friends at Basai is going to learn something that you don't know. Okay. Right. Second meaning, and this is very important as well, often neglected. It means the same thing as military intelligence. Now, I don't know if you watch a lot of movies, but when we talk about military intel, it's about pieces of information that are very expensive to acquire. Okay? This to be practical definition. It's just expensive piece of information. Okay? Why is it expensive? Because it's not given out freely. In fact, if you're going to get intel on enemy movement, in the old days you have to send Marines or scouts, right, deep into enemy territory with binoculars to say, well, what the enemy is doing? Are they creating a formation? Are they ready to attack us and so forth? What's the price you pay? Well, that guy's get caught, he's dead. So that's very expensive. Okay, that's very expensive. Okay? Now, that meaning of military intelligence has association with clandestine, right? It's something that's sort of like secretive, probe and dagger kind of thing. Well, nowadays you still have that. But mostly in the world of business, you have this thing called business intelligence. Okay? So you would think that business intelligence, in analogy to military intelligence, is about getting intel on your competitor, right? So, Android would like to know, there's so many Android manufacturing competing, right? And also they're competing with iPhone, obviously. They like to know what sort of new feature the other company is going to release in fall, in autumn, right? So we can get a leg up on it. Okay? Either have a version of that feature, or sort of like, create a sense that that feature is not as important as this feature we have or something. Okay? So that's what's called business intelligence. Now, with military intelligence, because the chain of command within the military organization, the military intelligence is about your counterpart, your enemy. Okay? With business intelligence, however, there are more subtle form of counterpart. So business intelligence is not about just finding out what your competitor is doing. It's also finding out what the economy is doing. Because your business lives inside the economy, right? What's the global trend? Okay? So even though you're doing some product that has to do with adults as your consumer, you also have to monitor TikTok to see, what the children or what younger people are thinking. Okay? Because that will maybe set the tone of the consumer space. I don't know, right? So the environment, the society, geopolitics, that's also business intelligence. What else? Well, intelligence on your own employees is also important. That's why they do, I don't know if your parents are in corporate world, but they do this sort of thing called, 360 or employee engagement. Why? Because if your employee are not engaged, A, they'll just leave, right? And B, they would not be that productive or creative. They reserve their creativity elsewhere. So if your employee is engaged in the value or the mission of the company, they'll apply their creativity to business solutions. Otherwise, they'll just clock in 9 to 5 and reserve their creativity to weekend photography or something like that. Okay? Now, I'm obviously simplifying the situation. But that's what business intelligence is all about. And this is also part of your, education in Basai. in data analytics class or in entrepreneurial business management. The idea of business intelligence is very powerful, okay? But it's not the main of my presentation or this class, so I'm going to skip over. Finally, intelligence means computational intelligence. Now, my Ph.D. at Imperial was in computational intelligence. And let me just elaborate a little bit. In my days, computational intelligence covers sort of like three interrelated areas. One is artificial neural network, which you see is the core of today's AI. It's about machine intelligence, how to get machine to be intelligent, but not necessarily to mimic human being. So we don't care that the computer gives response that sounds like human being, but we care about if the computer gives us optimal solution to a problem. Okay? So we acknowledge it's a computer, but so this is intelligence that has to do with the quality of the problem solving, quality of the solution. It is computationally derived because this set of model, even though it starts with mathematics, incorporates statistics, at the end of the day, it's going to be done on a computer. Okay? And some of the computational model takes a lot more of a simulation flavor, so it's a little bit less of a mathematical statistic. It's more like what's called Monte Carlo simulation. But anyway, you don't have to worry about that. The point is that you want to get intelligent answers. You don't ask a human being, you ask a computer. That's what it is. Okay? And it's the first meaning of that. A second meaning is this form of intelligence that is inspired by nature. Now, you are here because you're a product of gazillion years of biological evolution. Okay? That's how we came from mammals or invertebrates or single cell, very basic multicellular organism. Well, so obviously, the way evolution works gets you to something very good at solving problems, right? So you get, that problem is called survival, okay? That problem is not to create a human being that create university, no. The problem, let's forget human being, let's say a butterfly, it's creating survival for butterflies, it's solving solutions for what plant can operate in highly acidic soil. That's a problem. Survival in highly arid, acidic desert. Okay? Surviving in very dense jungle, very little sunlight. Those are all problems. Nature solved it, not with engineer, but with trial and error and, recombining solutions. Well, very clever people. One of the legends in the area was my own supervisor, who passed away already, sadly, at Imperial. But anyway, it's about, hey, can we simulate evolution in computational algorithm? Except, instead of survival as the goal, let's say the goal is how to travel in the least amount of time from here to there. Okay? Here to there, I can take this path, I can take that path. Some path is longer, but faster because there's less traffic. Some path is shorter, but, well, maybe for this period, yes, it's good. But for the other period, it's bad because the traffic is terrible. Okay? This is a problem. Well, let's do this. Let's put this as a task and then simulate population of animals, say computational ants, okay? And see the ants that follow the right sense of travel, like always take the long path, always take the shortest path, always turn right, or go to the path, try to go straight, but if it looks heavy, turn left. If it doesn't look better, turn right, and then try a few more, and then check again. So these are rules-based, right? We can evolve this. and get at the ant that is so smart at solving computational ant that's very good at solving traffic problems. This is called evolutionary optimization. This is like 85% of my thesis is about this sort of thing. Third sense of computational intelligence is about, well, you know the computer can use good solution. Thing is, computer is very picky. It only operates on mathematical data, right? Certain things is human being, right? So this whole thing about translating human concept of happiness or hot, cold, or cool, or I feel a little bit chilly, you know. How can I turn on thermostat? Okay. Now, there's like mathematical mapping that maps from human language to machine input, like turning on the air conditioner or turning it down. So it's like fuzzy logic, cybernetics, some of you may have heard about that. It's basically about symbiosis between human and machine intelligence. Okay? So human may have a little bit less intelligence in terms of coming up with good solutions than computer, but hey, computers are very good at knowing humans are very good at knowing what they need, because after all, we want it to serve human beings, right? So we don't want clever solution that's good for computer, we want clever solution that's good for human being. So this kind of like symbiosis, cybernetics, connection between human and machine, man-machine interface, that's called the third meaning of intelligence. And now, because everything is digitized and all the information is digitized, we kind of like push this term out in a way, so we use the term digital intelligence. Hence, in BASA, you have applied digital intelligence concentration, right? Because everything is digitized. So, you know, even when you say, I feel a little bit chilly, it's not a human word anymore because it's actually a digitized word. And when we get to the large language model, we'll see how this thing is like, you know, completely the paradigm today. Okay, so having covered the I in AI, so let's talk about A. I'll do this very short. Well, A actually means artifice, meaning that it's a creation by humans. So that's like a first meaning as well, right? Correspond to the after the World War II, say Alan Turing thing, hey, we created a computer. Okay, so that's an artifice. Okay, it's an artifact of human engineering. Okay. Second, the meaning is artificial semblance. That also is the sense, in fact, that's the principal sense that Alan Turing used, in the sense of artificially resembling. So it's artificial because it's on the device a human being creates. It's artificial because, well, it kind of mimics, hence imitation game, right? Finally, and this last line is actually only added in the recent generation. Art in this case means, artificial in this case just means artful creation. We are getting to the stage where the truth is not being learned by the computer, but the computer is creating the truth. Now, this has good and bad meaning. Good meaning means computer can get into creative space. Bad meaning, computer can create fake news. Bot can create fake news. So, the truth or what is considered intelligent or what is considered worthy of human conversation is completely created by machine. So it's not a machine, it's a creation of human being. But truth, beauty, conversation, marketing trends is created by machine. It's artificially created by machine. Yeah? So it's manufactured truth. Whatever is trending, what's, you know. So this meaning of artful creation, if you are a TikTok influencer, you can help do it. But if you're not a TikTok influencer, you can program a bot to do it as well, right? So you can be on a Instagram promoting particular trend with Panama hat, whatever, okay? Or you can create a chatbot that does it. right? So the A in AI. So that's why you need to study A in context. Okay. Now, the machine learning in AI. Now, this is not a machine learning class, right? But in fact, 2 weeks from now, again, in the spirit of learning under the hood, you will learn about machine learning. Okay, so I'll reserve this for that class. But again, like we saw in the beginning slide with the Venn diagram looking thing, machine learning was motivated by the need to program a computer to learn and acquire intelligence. Now, okay, I'm not going to read through this, and again, I'll make an exception that I will give you a handout today, and that's this set of slides that you can use, okay? Despite, again, my protest of not giving student, it's a terrible discipline to give student handout of a presentation. Okay, students should write their own notes. In fact, when I was undergraduate, this is a good discipline. I'll give you a side story. I think this was only, for some reason, this was only done in my physics class. Right, in my physics class, again, back then, lecturer, and we just come in with a piece of chalk and maybe a book under his arm. Most of the time, the book he's written. He writes the thing on the board, okay? And I take notes. We take notes. There's no handout, okay? So you are forced by the rule of the game to tune your attention to what's being spoken, what's written, and what you're writing. And here's the cool thing. On final exam, we are allowed one sheet of paper. We can write anything we want. Okay? Here's what I found out. I spent a lot of time organizing the knowledge and obviously squeezing them into tight spaces, because the more you can pack in a piece of paper, the better, presumably, right? Well, some students, some people did this by sort of like using a syrup machine, right? Just keep shrinking, and you don't know what a syrup machine is? Oh, you do. Okay, keep shrinking until you get a smaller one and you cut and paste. And they didn't do so well, I don't think, in the exam. But I did, well, I did better than I would have using this method, which is to write both the outline and particular details that I needed for that physics class. I don't care if it's thermodynamics or special relativity or maybe electromagnetic. It's kind of like summarizing one piece of paper, right? Summarize, and I take to exam. Okay? Here's a funny thing. Almost always, I never look at the piece. I never needed to look at it during the exam, because the process of doing this kind of crystallized the idea. So I learned to do this for my economics class, even though in economics class I wasn't allowed. I think if I recall correctly, I started to do this for all other classes, mathematics and all kind of stuff, even though the rules are different. Okay, so anyway, take your note, but I'll make an exception. I'll hand this to you. Again, definition. Again, for midterm, if you were to use this and Xerox, if it's small, it's not going to help. But if you write it yourself, yes. Okay? But, this thing is not very good. Why is it going back? guy. Huh? And be a little patient. I think it has to do with got stuck somewhere. We can edit this out, no problem. Okay, right. All kind of stuff. Enterprise analytics. When I was many of you would know that I didn't start my career as an academic. So I was working for the Bank of Thailand, and I was first senior vice president at a commercial bank. And what I was doing there was called enterprise analytics. It's like kind of data analytics, but applied to the whole enterprise, whatever problem they have. So basically, anything mathy, something that bankers and accountants couldn't do, find that way to my desk. Right. Okay. So this is where we get to historical or techno-historical. This is a very long arc of man-machine symbiosis. Okay? I mentioned a little bit about the third leg or the third sub-branch of computational intelligence about symbiosis between man and machine. Well, in that sense, that machine is computer, right? In this sense, machine is anything that's not that's created by man. That's not nature. Well, about 3.5 million years ago, we had the stone tool. Those are the picture. They're not natural in the sense that the earliest stone tool was just found. Maybe our ancestor found a piece of stone that was very sharp enough to make a weapon, right? To use as a weapon. But pretty soon they realized that hey, you can shape it. So even though the stone itself was found lying on the ground, our ancestor didn't just use it as was, maybe in the beginning, but they learned how to chip, little sharp edges to it. By the way, do this for all your presentation. Always acknowledge the source. Okay? It's good manner, protects you from plagiarism issues, and it's a way for the audience to shake up the, let's say one of you happen to say, hey, that's a good thing to learn about, this long qui or whatever, 3, okay? So go to this link and then learn some more, okay? This is how you expand your knowledge. Well, I would argue that for modern human beings, not prehistoric, but it starts with this guy, well, not this guy, but around that time. It's the 13th century. The minute we started to have eyeglasses, it becomes an extension, right? So human biological function is basically enhanced, okay? There's a concept called transhumanism that you may or may not learn in some of the project class, perhaps, I don't know. Okay? This is when you take this thing to a gazillion degrees. So you can have microchip implanted, you can have for amputated persons, you can have exoskeleton framework. Anyway. Next thing that you should like to know is this thing called, you guys, I don't know if your parents collect expensive watch, but anyway, one of the brands is Jacques Drouot. Well, they were not famous for just making watches, but they're famous for creating this automaton. This little guy here, it's called automaton, right? And this was 17th century. And here's a cool thing. You give it something to write. Let's say, love you, okay? And this machine, mechanical, okay, has a robotic arm that sort of like goes to dip the ink and write, love you. Pretty cool, huh? And this was 17th century. Now, the next breakthrough analytical engine. I think this one sits in the Museum of Science in London, South Kensington. Actually, it was basically next door to Imperial College. So, if you go to London, I encourage you to go there. Well, you talk about mechanical things that add, subtract, and that's not so impressive. But how about multiply, integrate? You know, that's very advanced applied mathematics with a computer. But this computer is done using gears, right? Gears. So think of a Chinese abacus where you have this kind of mechanical representation of numbers. But anyway, it's very clever. Right. Well, that's a little bit too far out. So let's come back a little bit. Now, AI. Now, this is going to bring you to modern time. There are two AI timelines. Okay? There are two AI timelines. Okay? That I want you to know about. One, there's going to be more in the future. Okay? But these are the dominant timeline that you need to know about. One is called visual pattern recognition, meaning, well, this thing about computer that can recognize objects. Well, how did it start? It starts in the 50s, 60s. Okay, with Hugo and Rizzo experiment, and we will do this. By the way, I'm going to teach a class, so like talk for like 2 hours only. The last hour I would reserve to maybe watching some video that I think you should, and one of it is about this. Basically, it's it sounds cruel, but it's not. You just sort of like put a cat head. Make sure it's looking at a screen, and then you use electrode to measure the brain activity, and then you show different things to cat and see if it responds. Okay? And you see in the video, but I'll just give you a heads up. They try to give it a picture and see how cat responds, because cat can obviously recognize faces. It doesn't work. Cat has no response. A particular neuron, I mean the whole cat does recognize, but the neuron that's linked almost directly to the visual field doesn't recognize faces, doesn't. And then I think by accident or whatever, they just bump something or they move some, and there's a line. You know how those old movies have like lines and stuff? Well, when there's a line, the cat neuron lights up. Right? And that became the basis understanding that visual recognition begins at the bottom layer from sensing if there's a line. A line meaning black, white. Okay? Or a line, black, white, that sort of primitive shape. And, long story short, we get to your iPhone that recognizes faces. Okay? But this mathematics, and going back to the concept of this hockey stick I told you, this inflection point of computer being able to do human-like visual recognition tasks only happens, the inflection point was in 2010, 2011. Okay? I can pinpoint you to the day, almost. Well, it's not the day, it's a conference. Okay? But this is the cool thing. And this is where this concept of conference happens. You guys are so fortunate because of this conference. You know, the mathematics behind it was conceived in the 80s. And you see a little bit. It's Professor Fukushima, who doesn't get recognized today, by the way. Because he wasn't the one, he wasn't the team, he didn't lead the team, it wasn't his student and him that made this inflection point in 2010. But the mathematical formulation, basically, of neocognitron, this is a word you don't hear anymore, but basically neocognitron was the sort of like precursor of convolutional neural network. And it's sort of like a computational model of how the cat's visual cortex works. Okay? And 1986, this was the beginning of what's called, so this is multi-layer perceptron. Again, this is not machine learning class, neural network class, but you learn a little bit of engine and the clue. Multi-layer perceptron is still here today. Okay? It's still here. It's inside ChatGPT. It's not the beginning, the middle, but it's sort of like toward the end part of a lot of large language model, visual recognition, convolutional neural network. There will be multi-layer perceptron stuff in there somewhere, sort of like a workhorse. This was, you notice, Rumelhart, Hinton, and Williams. Some of you may recognize Hinton is very famous now, right? You look at YouTube, you say Hinton is the father of AI. Well, he's not exactly father of AI, but you can say he's the father of the inflection point, because it was sort of like him, his colleagues, his team, and maybe other colleagues at near other university, okay? Jan LeCun and whatnot, okay? It's that cohort that gave you the inflection point, the explosion of this visual recognition in 2010. Okay, and that 2010 was this paper. Krzyzewski, Suskiver, this guy is still very dominant in the field today, and Hinton, same Hinton, right? So presumably he was very young in 1986, but in 2012 he led a team, his students. That's a convolutional neural network. That was the inflection point. That got you from this study of how the cat's brain works to this multi-layer. By the way, this is this bottom here. Sometimes you see that all the nodes are connected. You see something called fully connected layer. It's sort of like multi-layer perceptron, but a modern version of it. And finally, on the bottom right here, okay, on the bottom right here, you can't see it, but you see in the note, this image come in, there's convolutional layer, and comes to fully connected layer. So fully connected layer is a bit like the multi-layer perceptron. Convolutional layer is a bit like neocognitron. Okay? Yeah, we're not thinking of it like that. Okay? And that's how machine can recognize stuff. Okay. So this is the visual recognition AI timeline. Once you get to this inflection point, then it can do all kinds of things. This kind of image synthesis, so now it's not about recognition anymore, but about creating picture and all that diffusion model and DALL-E and whatnot. This came obviously way later. Not way later, but 10 years later. Okay? But this was preceding of Neuro IPC. Actually, I presented the paper, my paper is at NIPS. It's kind of like a smaller version of that kind of conference. Right. Second timeline. This timeline gained dominance, and this is the timeline now. If I were to give you this lecture 5 years ago, the predominant timeline would have been that slide. Now it's this slide. Well, this slide actually is even older timeline. Well, not older, but it's the original timeline of AI, started with Alan Turing. His paper, Seminal Computer Machinery and Intelligence. Okay, I encourage you to read this. It's a homage, but anyway. Here's the thing. You see this acceleration, 1950s, and almost nothing happened, and then you get this 2013, 17, 18, 19, 20, 22, 23, right? And now 24. What happened? Well, let me tell you this. So it's a quick story, but it's a very good insight. Think about it. Computational intelligence, computer can give you intelligent solution as long as it has an intelligent model and you give it the input, right? But the input that you can communicate with it, again, without this cybernetic fuzzy interface, is numerical. So you give it numerical value. then computer do numerical computation. Gives you back numerical. Okay? Now, that number can correspond to a temperature, and then you translate it to hot or cold later. It's up to you. The point is, computers do not speak to you in words. They only speak to you in numbers. So, the key paper was Mikhailov and friends, et al. And friends. Vector representation in vector space. You guys know linear algebra, right? What's a vector? It's a list of number, right, of fixed dimension. So if I were to ask you a geo-coordinate on a Google map, that's a two-dimensional vector because they put everything on the surface. Actually, GPS coordinate is three-dimensional, so that if you take a GPS, you can actually measure the height. You can, go to Mont Blanc and take an app and look at the elevation and altitude, right? So it's actually three-dimension. Well, what's good about dimension? Well, first of all, I can locate you by your coordinate, right? What else can you do? Let's say that you sit close to your friends. I can infer from that statement who likes whom and who doesn't like whom so much or doesn't know. By what? By taking the distance. Yeah? Right? Right? So, you are close friends if you're only arm's length away. But if you are across the room, maybe you don't know each other. Let's say, something like that. Right? So, that's what it means to be an object in a vector space. You, because you can't float, as far as I'm concerned, you only have two dimensions, right? You are at the front of the class, the back of the class, the left of the class, and the right of the class. Based on that, I can give you score, right? I can say class participation score is 90% for the first row, 80% for the second row, 50% for the last second to last, and 20% for the last row. I can score you just like that. I don't have to know who you are. Now, that's probably not very fair because you can have attentive student in the back and sleeping student in front. Okay? But as a proxy, as an information set, I can infer all that just from where you sit. Okay? If you go to in advanced economy, like in Japan or in Europe, class will fill from the front because the student will want to be in the front first. And then once that seat is filled, somebody who comes a bit later sits a little bit further back, right? People who sit in front get the better view, and it's also the most expensive seat if you think about it. But it's not the most expensive seat in an opera or in a concert hall because the acoustics not that good in the front row. But for lectures, for seeing little things, you see this, I don't know if you see this picture of Japanese or European or American lecture hall, see like that. So anyway, it's filled from the front. And that's basically a sign of advanced economy. Okay? If you go to a more backward country, so to speak, I don't want to name names, or say, whatever, you see that the front rows are virtually empty, and they fill from the back, you compete to sit in the back. And, okay. Right. That's a lot of information just from two numbers. Okay? Now, in my sense of it, two number meaning the number that's relatively front, back, left, right. Okay, fine. What's that got to do with all of this? Well, here's the deal. In order to work with numbers, you have to turn it into vectors. In fact, this thing called word representation in vector space. The short name for it is called word embedding. Remember that. Okay. Now, technically, they embed part of the word, but just say word embedding. What it means is this: English word. Let's say there are a million English words that are necessary to have a good conversation. Let's say you need a million word vocabulary to be a good language model. Every single word is first translated into 300 numbers. Okay, 300 seems like arbitrary, but it's a good size of a vector. What it means is that instead of 2 dimensions, the word lives in 300 dimensions. Okay? So, in order to identify a word, you need 300 values, basically. Okay? 300 values. Now, that 300 values also contains information, like which words are close together. Let me ask you this. If I were to look up 300 numbers corresponding to cat, and 300 numbers corresponding to dog, and 300 number corresponding to refrigerator, astronaut, ocean. Okay? Which 2 words do you think will have the 300 numbers that are close together in that 300 dimensional space? Cats and dogs, right? Because in context of human being, in the context of internet, chances are you see cats and dogs in the same context because there are pets, favorite pets, mammals, right? Whereas cats and astronauts, well, yeah, you can have astronauts that have cats, or cats that dress like astronauts, but that's not very often. So this kind of affinity is a good word, by the way. When I say that you like each other, that is a subset of affinity. Affinity means closeness, right? Affinity can be spiritual affinity, intellectual, conceptual, emotional. So if you like somebody, it's emotional affinity, right? But if you don't like this guy, but he thinks like you, then it's intellectual affinity. Okay? So it depends. In large language model, which is what all of virtually 80% of applied AI is going to be all about, is about contextual affinity of words. Okay? And that basically introduces word as something computer can play with. But how can computer play with words? We need a large language or language model equivalent of neocognitron. It's sort of like the first line of processing. Instead of convolutional layer, you need some computer architecture, some kind of neural network. Okay? Again, this is not a machine learning neural network class, but in 2 weeks you start to see the inside. Well, that thing is called attention mechanism. Long story short, you only make sense if you pay attention when you give a response, if you pay attention to what was said to you. Think about it, right? Now, we're talking about computer that give response that is human-like. Okay? Imagine if the chatbot gives human vocabulary, but completely irrelevant. How are you today? The moon. It's got nothing to do with it. It's not even close, right? It's not even close. Because it's not paying attention to what you said. But if it's paying attention to what you said, it would know that it's a question. And that question is just a greeting, so greet back. Fine, thank you, how are you? Okay? And this is how cool the technology gets. Because of this thing, by this paper, this Vani and friends, et al., attention is all you need. Attention is a way of the algorithm to say how or which word or how far back you should pay attention to. Meaning, the word, the 300 number representation of which word should the computer algorithm use. That's how it knows something like when you say, talk to ChatGPT and say, when was Isaac Newton born, or what day was he born? Let's say he was born on Friday, okay? And another sentence say, who else is born on that day? Right? Artificial intelligence has to refer back to something before, and that something before was Friday. Okay? And the word else means don't give Isaac Newton anymore. Maybe give Leibniz. I don't know. Give somebody who else in that century was famous, who was born on Friday. Okay? So it has to pay attention. That's what this paper is. It's a very clever paper, and one of the coolest things, in a scientific paper, it's always given in technical term. But once in a while, the authors are so confident, has to be very confident, that this is a game-changing. He or they, and only then, will give it a very catchy name like this in a technical paper. All you need is love, all you need is attention is all you need. That is the name of highly technical paper. And it was only given that kind of like friendly name because the authors were so confident that this is going to be like a meme, so to speak, right? Most papers are not named like that. Anyway, that thing gives the architecture, but not the horsepower. In other words, you need somebody with big money and room full of computers. And that's when you have this GPT 1, 2, 3. Notice this is the number of parameters. 175 billion parameters. Things of high school days when you were doing linear regression. Okay? When you're fitting a line, you guys remember that, right? You need two things, right? You need the intercept and you need the slope, right? You use data, a whole bunch of data, but basically the two numbers you want is the intercept and the slope. Those are parameters because they're calibrated by your data. Okay? That's what you could do with linear regression. Okay? Fit two parameters. The reason we have ChatGPT 3, 4, let's just go with this 3. ChatGPT 3 has 175 billion. Right? And if you're talking about, parameters. So what are the parameters? If you go back to this slide, sorry. You guys see this? Inside each node, it's like 1 or 2 parameters. Each line here is like a value, a parameter called neural network weight. So you can see why if you keep adding all these neurons, so to speak, this is kind of computational mimicry of a neuron. See? So look at this. Hey, you guys recognize this? Well, what's B? B is an intercept. Yeah? What's W? W is a slope. So it's almost like every single line contains a kernel of regression. Except instead of having one, you have a gazillion of them. So that's no wonder it can do wondrous things. Okay? Anyway, so let's go back to now. By the way, this thing that you see, this kind of linear, basically this thing is that. One layer of this is called a linear layer. So they can have many layers in here. Okay, it's not just one, by the way, it's a stack of them. It's just so big. Now they don't draw the little neuron, the little nodes anymore. They just draw a block. Okay? Well, in ChatGPT 4, these blocks contain 175 billion parameters that is calibrated from data. Now that data is from internet, basically. So why is ChatGPT so clever? It has basically the same, as much, well, not quite, it has less. It has so many neurons, not as much as in your biological brain, but quite close to it. But the number of connectivities is, very close. Pretty soon you'll have actually a computer that has more neurons than human brains. I think we probably have that already. I'm not quite sure. Let's check the number. Okay? But anyway, it's got so much parameter. Now, as you know, you cannot fit more parameters than you have data points. So at the minimum, you will need billions of data points. Well, fortunately, you have more than billions of data points because you have the internet. Okay. So why ChatGPT is so smart? It is a big brain that's read the internet. Basically, okay? As much internet as the team at OpenAI could digitize, which is virtually all of everything except maybe the dark web. Okay? The dark web is not as sexy as you think. It's just back-end thing, not very, okay? But for human understanding, the surface, the internet, that's big enough. You haven't read the internet, have you? Okay? You've read slice of slice of slice of slice of slice of internet. And ChatGPT has virtually read the internet. So that's why it's pretty smart. Those are the two timelines. Okay? Those are the two timelines. Now, this slide is kind of like ChatGPT blown up because this is how you understand ChatGPT, but I'll actually give you a separate lecture for that. Now let's move on. Once we got to AI, now we get to the G's. G. Okay? The first G you need to know is generative. Generative AI. Okay? Tell you what, interestingly, the beginning is called generative adversarial net, and this is really cool. Okay, pay attention to this because maybe in the midterm I'll ask you to give you the story because the story is so cool. The story is so cool. Okay. Right. The task, you remember the visual recognition task, right? Vision recognition task was to give it picture and the computer should give you identification. It's a cat, a dog, it's whatever. Okay? Or it could do something else, like numerical prediction. Give you a series of temperature today and yesterday and the day before and output temperature tomorrow. Okay? Now this goes under the rubric of supervised learning, which we learn about it in 2 weeks' time in a bit more detail. But the idea is that the AI, in this case, is a computer algorithm that looks at past input and past output and learns the function between so that when it sees the input, it has I may have said that. It gets fed a lot of input and output. So basically X is the input, Y is the output. X could be a series of numbers, Y could be temperature tomorrow. X could be pixel value, picture, Y could be cat. Think of it that way, okay? So, input, output, that has happened, or that is considered truth. The word we use is ground truth. Now, because we have fake truth, it's kind of sad. Anyway, so the ground truth gives you a whole bunch of input-output pairs. The idea is for the computer to learn that mapping from input to output, so that when it saw a new input it hasn't seen before, picture of another cat, it can give you the right output, which is to say cat. Right? So it's not good enough that it can match the previously seen cat, but if you give it a new cat, it would also know, oh, yeah, it's a cat, even though it has never seen it before. Okay? That's called generalization. Okay? How good is machine learning? How good is AI? Is the power of generalization. Okay? By the way, go back to your high school day, interpolation, extrapolation, all of that lessons apply. Some of the new input requires the machine to do interpolation, and it does really well. Some of the machine's input requires the machine to do extrapolation, and then it can get nonsense. Okay? But never mind. Let's go back to the story. This is a story, well, clever people realize, how can we improve the performance? How can we improve the performance of this algorithm? We give it all the data. That's all we could. But let's say the data, you only got like 10,000 images of animals. Okay? That's all you could manage. And the model doesn't do very well. Okay? Now this is the clever stroke of genius. How about this? How about we, or this guy, good fellow and colleague, create another algorithm that generates fake picture. Fake picture of cat. And use the output of that generation to feed into this thing that you are trying to teach to recognize cats and dogs. And then have them fight. That's the word adversarial. Net is basically the neural network. The reason there's S is because there are two of them. One is trying to learn the right identification method. See picture, oh yes, that's a cat, that's a dog, that's a teapot, that's avocado. The other one is trying to generate fake picture of all this. And they get score accordingly. The first network, I'll just call it first net, gets a score if it makes a correct identification. The second net gets a score if it can make convincing fakes. This is a story, guys. The story was to create a fake to help the first net is called discriminator, because it's discriminate between cats and dogs and teapots and avocado. Generate, discriminate, generate, discriminate, generate, discriminate, and have them fight. Now you don't have just 10,000 pictures to train the discriminator. You have 10,000 of the right, and you also have the fakes. So pretty soon, this guy gets pretty good. Okay? You reward the faker, but at the end of the day, who are you going to use? You're going to use the discriminator, right? And you throw that thing away. That's the story, guys. That's the story I want you to remember. Now, of course, what happens when you don't throw away the second guy? Becomes a deep fake generator. See that? They didn't start out trying to create a fake Obama. Okay? They started out trying to create a model that distinguishes Obama from Michelle, or Obama from Clinton, or whatever. Right? So it creates a lot of fake. It looks like Obama, but it's not. So that it has a sharper discriminatory power. In the end, if you don't throw the second guy away, that becomes a deep fake machine. Well, it turns out deep fake machine makes a lot more money than discriminator in some cases. Okay, so it's kind of like ironic. But that's what this deep fake is. Well, anyway, That is the birth of generative. The first time the word generative and AI or generative and neural network are seen together in the same context. Okay? The first time. Now, what about generative AI that you see today? This generative, maybe I should put another line. So, yeah, I did put another line. So that's generative. The first time the word generative comes in. And now we have what's called generative artificial intelligence. Now this is deliberate. It's deliberate. However, okay, I'll tell you this. If I were to build a model, remember I was telling you about a model that predicts the temperature for tomorrow? Yeah? If I were to ask a computer to take, historical temperature and predict tomorrow's temperature, okay, I get some kind of accuracy. Okay. How about this? How about I want it to predict not tomorrow's temperature, but the next week. This could mean a week from now, what will be the temperature, or every single day from tomorrow up to next week. So basically, long horizon. Long horizon. Okay? Long horizon. You can do two ways. You can do two things. You can formulate the problem as input the past and output the future in whatever horizon you want, say a week. Okay? Or, alternatively, you can say input the past, output tomorrow. And when you use this, you use the output that it predicts as input to predict the day after. Right? Just keep moving. Just keep moving. So use the output of tomorrow's prediction as input to predict 2 days from now. And just keep looping this until you get to the end of the week. Which one is better? Now, one little participation. Which one? Who do you think A is better? Who thinks B is better? A. Who thinks A is better? Who thinks B is better? Who doesn't think? Oh boy. Okay, let me give you a surprising answer. In a prediction problem, at least when I was a student, we were taught, we had to do the first one. If you want to predict 5 days from now, give it 5 days from now data as an output for the computer to learn. If you give it 1 day from now and keep looping back, it's going to go crazy. Why? Because the error is going to compound. The error is going to compound. Okay? So, for prediction problem, if you have a longer horizon to predict, you don't want to do this looping. It's going to be nonsense. Right. However, this is however, with language model, because it could be because of the variety of words, because of the context, it makes no sense for you to predict 5 words ahead in response. Makes no sense. First of all, you don't even know if the response is going to take 5 words. Maybe 1 word will be okay. But there are various other technical reasons why it doesn't work in the language model. So somehow it has to generate the first word, use that output, loop back, generate the second word without losing the plot. Here's the thing. Okay? So if doing something that in a prediction problem would be terrible because the error would compile. But it turns out that by, anybody want to impress me? Attention mechanism. You can keep generate things that still make sense. In other words, You give the computer the question, it generates one word as a response. It takes its own word as an input, generates the second word as a response. ChatGPT doesn't reply you in a sentence. It replies you in one word. It takes that word, feedback to itself, gives you another word. Except from this mechanism of call attention, it does this in a way that doesn't lose the plot because it pays attention to everything you said and everything it said. So it makes sense, okay? And this capability is generative loop. Okay? So this ability, first of all, you saw that neural network can do generative adversarial, but the generative in the second sense is what basically it's the same sense, but in a different context, if you want to put it that way. Or you can say it's a different sense. I don't care. The point is that in this sense of generative AI, what it means is that you get the AI to generate stuff. Feed on itself and generate some more. Just start rambling. Except with attention mechanism, it doesn't lose the plot. Now, finally, so this is the third part of the story. Again, you're going to write this in the exam. This is the third part of the story. Well, with large language model, you wanted to generate something that makes sense as a right answer, right? Now, think of something else. Creative process, painting. You don't want it to generate something that is quote-unquote intelligent because it's the right answer. In art, there's no right answer. Okay? There's cool and boring. Right? So there's no ground truth. So this becomes, hey, anything you generate is good. So this is completely free, guys. This is where the computer is let loose to be completely crazy. And this gets you this artificial truth thing where, hey, anything artificial is as good as truth, as long as it has right quality. Right? Think of it, abstract art. Right? It doesn't look anything like reality. Okay? Photography has taken over that job. But why do you pay a lot more for painting that doesn't look like reality than you do a photo print? Right? That is the truth. The truth is creation, is the truth. Now, in applied AI world, you are jostling that between freedom to create anything irrespective of the truth and giving response that's grounded in the truth. I would argue that, remember the thing I told you about how data is used to validate AI? Grounding the truth is your present challenge. Okay? That's a bit hard. That is a bit hard. That is the challenge that you face. Because this free-form, open-loop generation now is easy. It's a child's play. But generate free-form that, in a way, doesn't destroy the truth, but offer new insight, that is the gazillion-dollar AI. Think about it, yeah? You ask an AI to write an essay, one AI gives you complete nonsense, creative nonsense. Can't use that. You ask an AI to write an essay, it gives you a perfectly reasonable essay, but it's not going to win any contest because it just looks like all the essay in the internet. Okay, it's not inspiring at all. It's boring. Grammatically perfect, boring as heck. Wins no contest. So something that is an essay that's generated that speaks the truth, but creates a new perspective on it, I would argue that AI still can't beat a good human brain for that job. Okay? For the first job, definitely AI is what you beat because it's read the internet. It's got better grammar than you. It's got better thesaurus list than you. It's got better context-sensitive understanding of word usage than you, because it's read the internet. Okay? And if you ask it to give nonsense, it's also going to be better than you, because you're going to feel shy about giving nonsense. But to give something that is grounded in the truth, but completely novel in the insight, okay? Now, AI is working on that, so you better be good. So that's the G. It's called generative AI. Okay. Now, notice I had two timelines, right? So one timeline is about visual recognition, one timeline is about language. Well, if you think about it, if you want to create a Hollywood version of a humanoid robot, that robot has to be able to operate visually with audio signal, reading text, reading PDF, looking at picture, opening doors, all kind of stuff, right? These are called modes. These are called modes. So, the first step toward that is to have more than one mode. Okay, just like you have transdisciplinary, multidisciplinary education. In my case, I had bi-disciplinary education, physics plus economics. That's my bi-disciplinary education. But of course, as an undergraduate in liberal arts, I studied philosophy, mathematics, so other part is also multidisciplinary. Same thing here. First, you need an AI that doesn't work just with word, AI that doesn't work on picture, but maybe both. So that's where you have things like, ChatGPT, where you can import a picture as an input. And now you have to go to all kinds of things: sound, text, word, physical, maybe IoT, sensor data, maybe molecular representation of whatever molecular construction, so like bioinformatics information, biochemistry information, genomic, all kind of modes of input and output. So it's multimodal. Okay? And with this, think about it. How about if a computer has already read the internet, what else can it do? Well, it hasn't seen the world. It hasn't driven around. What if it's seen the net and also tags along on a Google map van? Right? Now it's getting insight from visual and text from, see what I mean? So you learn from Wikipedia, you learn from tweets and text and all that. You learn from riding along with a Google map car. Right? So the quality of information, the size of information gets bigger, and so is the output. So you ask the ChatGPT to what? Give you a response. Now you can ask it to draw a mind map, representation concept. Maybe pair up with DALL-E and say, okay, paint a picture or something like that, right? So, all of a sudden, with this, it's multimodal, so it's general in this sense. Okay, it's general in this sense. Okay, the first general is, the first word is multimodal. What else is the word general? It's also all domain of knowledge. Because now that it reads from scientific paper, not just Wikipedia, now it looks at, a street map. Its intelligence is not just about writing essay. It has a general form of intelligence. Because think about it. Would you be considered intelligent if all you can do is write good essay? No. In fact, you know about this, if you have like some kind of a medical condition, you become an idiot savant, meaning maybe you can't speak, but you can draw a gorgeous picture. right? Well, that's in a way not general, right? It's a brilliant picture, better picture than you can, a normal human being person can do, but he can't speak. It's very sad. Sad for him at least, but he does excel in painting, but not in speaking. Well, that would not be considered general in the sense of, operating across domain. Or somebody who is very good in accounting, okay, but terrible in relationships. You have or somebody who's a good lecturer. I can be a perfect lecturer, right? I give good, insightful lecture. But when you talk to me in the classroom, I abuse you or say, you are so stupid. I don't have a human connection. That's not intelligent across domain. Right? So general intelligence is multimodal, multi-context, multi-domain, multi-everything. That's why you call it general. Now, you can call it general AI, but because you got the generative AI already, they have to switch the order of the word, so they call it artificial general intelligence. So AGI. So basically, if the AI was good enough, if it gives a dumb answer, AGI is not good enough to give a dumb answer. It has to be intelligent, but not only intelligent in certain applications, intelligent in a wide sphere, multi-domain, multi-context, multimodal. Yeah? And that's where we're going. And in this case, the last frontier, I don't know if the last frontier, but another word to add, maybe, I don't know, your midterm, whatever. The last thing is, this general means that you can derive intelligence not based on human. What does that mean? Well, one thing is, if it learns mathematical formula, you can say that even though mathematical formula is created by man, in a way, math is its own reality. But think about this. You guys heard of AlphaGo, right? Okay? You should leave Basai if you haven't heard of AlphaGo. Literally, quit Basai. Okay? Well, you know what AlphaGo? You know how AlphaGo got to beat, Lee Sedol or whatever? You know how AlphaGo was very good? First of all, it was multimodal. Well, not multimodal, but it looks at videos. So it doesn't have to be programmed with format data. It looks at videos. Extract from that video pattern of play. So AlphaGo learned from videos of human games. Right? AlphaGo. Now, what if, in the same spirit of generative adversarial, you set two computers that play each other or generate games by playing each other? I'm not quite sure exactly the modality or the architecture or procedure. So could say two computers compete, or two computers compete and generate the game so other computer can learn it. The whole point is that it's not learned, it has not, the second generation of AlphaGo did not learn from human games. It learned from computer games that play computer games. Sorry, let me say it again. It learns from games played by computers rather than games played by humans. What's good about that? Well, the internet maybe has 100,000 human games. But if you have a computer-generated games, you can have 1 million, right? So, this second generation, I don't know if it's called second generation, I don't know what the name is, but this generation of AlphaGo is trained on games played by computers. And this second generation thing beats the first generation something like 99 to 0, something, I don't know, something ridiculous like that. Maybe 99 to 1, I don't know, maybe 100 to 0. I don't remember. So now the intelligence is not from human now, right? Forget trying, I think this thing is stuck in reverse. Forget trying to learn from human games or human intelligence. It's learning from its own intelligence. Okay? So this is maybe the last meaning of general that I would impart with you. Okay? So just to give you a heads up, you know, midterm example would look something like, how many ways do I mean by general in general intelligence? Okay? If you say general because it's multimodal, okay, that's one. What about the other definition? That's very good. Okay. I don't know. It's something with the keyboard, I think. It's not really. Okay. Right. There. Okay. By the way, this should be your tools as you go in. I'll leave this to Marcos and all that later. But this is basically the go-to place nowadays. It's called papers with code. What it means is that it's got paper for the technique, but instead of just giving you how to, it actually gives you the code that you can copy from. See, academics are very generous. Okay? All of this makes a lot of money, but they don't just patent it. They literally give you the code. Okay. Finally, before we go to a section where we watch a bunch of videos or take a break, what do you mean by apply? And this is to set the. This is kind of like not part of the talk now, but to set the tone for the rest of the class. What do you mean by apply? I would argue that there are two kinds of applications. Okay? When we talk about application, it means something like apply AI to finance, apply AI to oil and gas industry, apply AI to fintech. So those are application areas. Okay? We're not talking about that. That's your job to learn in project, in capstone, and whatnot. That's not our job. That's not my job. That's not Marcos' job. The sense of apply, and this by all means may not be comprehensive, but I kind of group them in two things. First thing is, how can we apply AI as a feature? And this goes back to what I said before about, what would this class be like 3 or 4 or 5 years ago? So AI as a feature. So adding AI, like adding a chatbot, adding a visual recognition, or you have a project in sustainability, you want to do recycling, upcycling, and you want to have a machine that connects with a robot that sort out different kind of plastic, and therefore you need a convolutional neural network to identify PET from other kind of plastic, or from metal, or big chunk from small chunk, or food waste from clean plastic, something like that. That's when you say, okay, I need a chunk of AI as a feature, as a insight. Chunk of AI, okay? So it's gonna kind of appear as part of the solution, part of the product. So I would call it AI as a feature. So in this case, example would be you would be a developer. You use it in your app, okay, like a chatbot, a recognition classifier, or something like that, okay? So that would be how one way you apply the app, the AI. The other way, which is going to become increasingly more of a class emphasis. In fact, maybe in this class of yours, this emphasis may be 50%, maybe even 40, maybe even less. But I would bet that next year's class is going to be like 80%. Okay? And that is AI to help you do stuff. So it's AI as co-pilot. Okay? Co-pilot is a much abused term, but it's for now I just use it. I guess it's a good word as any. For example, you're a developer, you're writing code. But sometimes you get stuck, so you don't know, you just ask ChatGPT to write the code. Now, it's very good to get the ChatGPT to write codes for you, but don't ask it to be the final editor, guys. It's going to be terrible. Okay? So when you get stuck or you want to get something going, I do that. Even with I do programming in mathematics. I ask you, write the mathematical code to do this. It gives you something, and I should use this function. I'll look that function and maybe I'll rewrite from scratch. So I don't rely for a finished product. But to jumpstart the coding, it's very good. Okay? And also, another thing you can do is you go to paper with code, you go to you copy the code, and you go through, you can't understand this piece of code, you can copy it, put it in ChatGPT and say, please explain what this code does, or something like that. Okay? So yeah, don't use it to fine tune, but certainly to jumpstart, to help you, good. The other use is knowledge worker. Okay? When I say knowledge worker, basically, anyone who doesn't physically sweat because you work in an air-conditioned room in front of a computer. Well, you use internet, right? You do Google search, but Google search is not context aware. So basically, you ask ChatGPT to do Google search for you. So it's kind of context aware, and you set the context. Okay? And this is where I said, this attention, this memory. By the way, memory is a more technical term of attention, perhaps a more general term. But memory, attention is important because the ChatGPT has to remember what it is you're looking for. Help me look up this new market in Malaysia or something like that. And down the line, it still has to know that, we're talking about Malaysia, we're not talking about Cambodia. That's right. And I use it as a spell check. I don't mean by spell check literally, although I did. In English, there are certain terms that you use two different words, slightly different, and they're both grammatically correct. But you don't know which one is more global. You know what I used to do? I literally put that word in the code. So for example, if I want to use operations, research, which I think was the original term, but maybe somehow modern day people use operational research. Okay? When I was doing master, my degree was called operations research, but in UK, right, I skipped from the United States, I started Ph.D. in London. In UK, they call it operational research. So if I want to use it in a technical sense, maybe I'll put operations research in a double quote and do a Google search and see how many counts. Right? So I see how many friends I have. So maybe operations research may have 3.5 million, but operational research may have 7.2. I don't know. I would use the one that's more frequent, right? Same thing. Because ChatGPT has read the internet, basically. It does smoothen your narrative, your composition, your vocabulary. And in fact, I do this now. Okay? So if I have a term that I want to say something like precise engineering or engineering precision in this context, I literally now go to ChatGPT for that. Okay? Should I use precise engineering or engineer precision to describe microchip manufacturing? That's what I use it for. Okay? In that case, I don't have to worry about ground truth because they're both true. They're both good words. But the ground truth is in the frequency or in the context or in the human usage. And because ChatGPT has read the internet, it's going to keep a good one. Okay? So it's kind of global consensus, societal consensus. This, I think, is a tool for master student researcher, because at some point you're going to have to be a researcher, whether or not you realize it or not. And because there's so much material, you're going to need help in sort of like sometimes summarizing a little bit, okay? Now, that doesn't mean that's all you stop. Sometimes you get a synopsis and then you dig deep and then you go read the entire paper yourself or watch the entire YouTube. But it's a good way of getting a lay of the land. So, because researcher gets overwhelmed. We used to complain that we don't have enough material to go on. Now we have too much material. Okay? So use a ChatGPT to maybe prioritize, summarize, organize the survey activity. That helps. So this will be kind of like AI as your mate. Okay? And that's it. So let's take a 5-minute break. And when we come back, we're going to watch some YouTube and I'm going to narrate. Okay, Cap? So that's the end of this lecture. Let's watch on YouTube, but you know, it's not going to be so much fun because occasionally I would need to interrupt the flow. But this is the Huber and Riesel cat experiment. It's very short, so I'll let this thing play.
The researchers actually listened in to individual nerve cells firing in the anesthetized cat as they presented it with different visual images.
When we started working, Torsten and I, in the late 50s, we set up our first experiments, and they didn't go well because at the beginning we couldn't make the cells fire at all. We'd shine lights all over the screen, and nothing seemed to work. And rather by accident, one day we were working, and nothing seemed to work. And rather by accident, one day we were shining small spots, either white spots or black spots, onto the screen. And we found that the black dot seemed to be working in a way that at first we couldn't understand until we found that it was the process of slipping the piece of glass into the projector, which swept a line, a very faint, precise, narrow line across the retina. And every time we did that, we'd get a response.
Yeah. So I gave you a wrong story. I said in the beginning they tried pictures. Actually, they were more clever than that. They just started something primitive. But by primitive, it means like a light spot, right? And the artifact that gave it the line was I just spoke. Okay. Yep. The artifact was that they were giving the slide, and every time you put in the slide, there's a line. Yeah. So that basically was it. That was the scientific discovery. So let's watch another one. Now, this is a bit long, and I might skip some of it, but you only need to know this guy. Okay. The other two are also very important, but definitely Alan Turing. I'm just going to let this play through because you can appreciate it.
But merely looking at a computer won't tell us very much about what it actually is doing. Neither will it tell us anything about the revolutionary material and intellectual effects of such machines.
Have you guys ever wondered how Siri and Alexa communicate with us? How do they integrate with our smart homes and entertainment systems to automate our daily routine? How do face recognition or biometric systems work? How will self-driving cars be able to drive safely through heavy traffic? Well, it's all thanks to artificial intelligence. All these technologies incorporate artificial intelligence scientists to move forward with the idea of creating an electronic brain. In this video, we are going to has evolved into a powerful 1912 to and act like humans.
Okay, let's start
Alan Turing, June 23rd, 1912 to June 7th, 1954. What's up?
Hi, Gerard. We brought you here today to...
British logician, mathematician, and cryptographer Alan Turing is often known as founding father of artificial intelligence and theoretical computer science. Sometimes he is also referred to as the father of modern computer science. During World War II, his work breaking the Nazi Enigma code was quite famous. Due to his work, he helped the British to win the war and the invention of the computer. He was much ahead of his time. In 1950, when a computer had just come into being, Alan already started thinking that a machine could think like a human. He published a paper in...
Okay. Right. Alan Turing. First of all, go watch a Netflix or something in the Imitation Game. Okay? According to some very decent estimate, he shortened the war by about 2 years. That's how many lives he saved. okay, by cracking Enigma code. And cracking Enigma code was amazing. And this also led to the invention of computer. Now, something you don't know, okay, if you skip forward from the imitation game to what I talk about today, which is his inspiration for AI, you will have skipped the middle part. I don't know if it's the middle part, but he actually basically invented computer science. It was, back then, computers was not anything you could take for granted. What kind of electronic circuitry was going to create a computer? It's going to be 0 and 1. Okay, fine, maybe that was known, that you need to do 0 and 1 because computer can do switches. And that's it, right? So you need things like von Neumann. He invented what's called a computer architecture. Basically, all the computer you are using today, including one in your iPhone, follow what's called von Neumann architecture. But even more fundamental than that, the idea of what can be computed, okay, which is very esoteric, computer science, fundamental, very nerdy, mathematical stuff. What does it mean for computer to know when to stop, that sort of thing. Decidability problem. These are something that way above my head. That's Alan Turing. Okay? So this AI inspiration, in terms of his career, maybe would have been a footnote, but it's amazing. It's just he's way ahead of his time for so many ways. Okay, so father, grandfather. I mean, Jeff Hinton. Yeah, maybe you call it father of modern computing, but basically it's his cohort and a whole bunch of people before and after him. But this guy definitely was a singularity. It's like boom, there's Alan Turing. So, amazing guys. Okay, download this and read.
In 1950, in which he suggested a test, initially known as the imitation game, which is now known as the Turing test. The idea was to conduct this test to check if machines have intelligence or not. There were hardly any believers for the concept at the time, but now we can see that artificial intelligence actually exists. The Turing test is one of his best works, and has a significant contribution to the field of artificial intelligence. Alan Newell. March 19, 1927 to July 19, 1992.
But the brevity of that, these guys are all
earliest proponents of artificial intelligence. He was born in San Francisco.
Okay, these guys are all important, but please watch on later because we kind of are running out of time. I want to show you something else. There's Alan, there's Marvin Minsky. Oh, all kind of stuff. Okay, so let's see if I can go to. By the way, brief note.
1927. Machines have intelligence.
Okay. YouTube sometimes got very good content, but sometimes the accompanying video is kind of out of context. I told you that the three things, right? There's his work during the war, right? The Enigma machine cracking the code. There's his foundation of computer science, and then the AI, conception of AI. This is actually has more to do with the foundation of computing science. This is basically a computer. Okay, the idea is if you give a computer a string of 0 and 1, can you make sort of like kind of computer decide what to do or know when to stop, that kind of thing. So this is very deep. This is not AI. This is not to do with, well, not yet anyway, with AI. And also this picture here. Okay, that's actually the Enigma machine. That's the German encoding. What's so difficult is that when you enter a letter, it gives you another letter, right? Except this code is not static. So if you push P, it may give you an X. You push P again, it gives you a Q. So, and the combination is set by those rotary rings. So this is actually, I think, a real picture of either a replica or an actual Enigma machine. And they don't have a picture. Go watch the imitation game. You see the whole picture. So this is not AI, but definitely AI is that paper. Okay. I want you to watch. This one we watched already. This one is it's not very. Again, this is all very old technology. This is Fukushima. By the way, Professor Fukushima has been in Thailand. I met him. Very nice, very humble man. Met him during a talk, Python Thailand, I think it was. I was giving a talk, so he was a guest. Oh, sorry. Neural network. Okay. First of all, let me tell you, the word neural network briefly. Neural from neuron, like a brain, right? Your neural cell. Network because the neurons are connected in a network, right? Technically, it's called artificial neural network because biological neural network is your brain. Okay. So it's a model of visual pattern recognition. So think of creating cats, visual cortex, neocognition. Okay.
Reading a book, distinguishing faces, or understanding speech. All these things we as human beings can easily do. But it is very difficult to design a machine which can do them. Many scientists and engineers have tackled this problem, but they reach a deadlock when they want to design a machine which has the same ability as a human brain. Then how can we make a breakthrough in this problem? We believe that the best strategy is to learn from the brain. We are studying the mechanism of visual information processing in the brain and trying to use it as a design principle for new information processes of the future. There are over 10 billion neural cells, or neurons, in the human brain, which have complicated interconnections and which constitute a network on a huge scale. Let's watch what is going on in this network. Recently, neurophysiologists have discovered many new facts about the mechanism of the brain. In the visual cortex of the cerebrum, for instance, neurons are found to respond selectively to local features of a visual pattern, such as lines and edges in particular orientations. In the area higher than the visual cortex, it has been found that cells exist which respond selectively to certain figures like circles, triangles, or squares, or even to a human face. Accordingly, the visual system seems to have a hierarchical structure, in which simple features are first extracted from the stimulus pattern, and then these features are integrated into more complicated ones. Such a neural network is not complete at birth. It gradually grows, adapting flexibly to circumstances after birth.
Are you looking to establish your business using an address other than your home? Well, at
Sophisticated brain functions such as learning, memory, and pattern recognition are believed to be acquired through the growth of the neural network, in which neurons expand their branches, making connections with many other neurons. Based on such physiological evidence, we have studied how to synthesize a neural network model which has the same abilities as the human brain. As a result, we have succeeded in developing a model called the neocognitron, which has great ability to recognize patterns. The neocognitron is a multi-layered neural network consisting of a cascade of many layers of simplified neural cells. The connections between the neural cells are modifiable and grow gradually in accordance with stimuli given to the network. A repetitive presentation of a set of training patterns is sufficient for the self-organization of the network. The sum of the cells in the network becomes selectively responsive to each of the training patterns. Thus, the neocognitron, like a human being, has the ability to learn. Then let's see how the neocognitron recognizes patterns when it has finished learning. If a pattern A is presented to the input layer, only the one cell which corresponds to pattern A is activated in the deepest layer. This means that the neocognitron answers that the input pattern is A. If pattern B is presented to the network, the signal flows through different paths, and another cell corresponding to pattern B is activated in the deepest layer.
Okay, so this is ultimately how it works, but I just want to highlight the fact that in the first layers, it only detects like presence of lines. Okay, and then this combination of the first layer information becomes something more complicated. So at the end, when you get to the later, then you get a concept of, well, this neuron will fire if you see a curve or something like that. So it's something more complicated. So shading, curve, everything. So this is, I don't know how realistic the layer organization is in the human brain, because yeah, we probably have some layers, but sometimes it's just a bunch of things together. But in computer architecture, it's kind of like a practice or taken for granted that it's organized as layer. And once you organize them as layer, the whole 5, 6, 12, 20 layers is called a block. And then it's organized as block. So that's why you get to see those diagrams. Okay, but obviously in the human brain it's more organic. It doesn't have that kind of picture.
Even if pattern B is shifted in position or deformed in shape, the same cell in the deepest layer responds. In other words, the neocognitron recognizes the shape of the pattern independently of its size and position. Let's see in more detail how information from the input pattern is processed in the neocognitron. The input pattern is first observed over a narrow range by cells in the lower stage, and several local features are extracted. At the next stage, these features are combined by observation over a wider area, and higher order features are extracted. This operation is applied repeatedly through the cascade connection of a number of stages. Consequently, each cell of the higher stage integrates all the information of the input pattern and responds only to one specific pattern. One of the distinctive characteristics of the neocognitron is that positional errors of the stimulus features can be tolerated a little at a time at every stage of feature extraction and integration. In order to see this process, let's take a look at the detailed structure between two adjoining stages in the network. The feature extracting cells in the network are called S cells. After each layer of S cells, a layer of another kind of cells called C cells is inserted. Each C cell gets signals from a group of S cells which extracts the same feature but from slightly different positions. The C cell is activated if at least one of these S cells is active. Even if the stimulus feature is shifted in position and another S cell is activated instead of the first one, the same C cell keeps responding. Hence, the C cell's response is less sensitive to shifts in position of the input pattern. In the whole network, layers of such S cells and C cells are arranged alternately. The operation should tolerate the positional errors a little at a time in each stage, rather than in one step, plays an important role in endowing the network with an ability to recognize even distorted patterns.
Okay, just to make use of time. By the way, looked up. Human beings have about 80 billion neurons, but what matters is number of connections. It's about 100 trillion. So the latest GPT-4 is not even close. Right. Okay. So this is actually the very first the landmark event. This is identifying digits. So you can see the digits start from combination of curve, right? So you can see this presence of vertical line, presence of horizontal line. The important thing that was very difficult was have what's called positional invariant. In other words, if the line is here or here or here or here, you can still detect it. Traditional multi-layer perceptron couldn't do that, but this convolutional layer, it's kind of like scan. It does this kind of scan, so it doesn't matter where, and that's very much a function of human cognitive learning. Let me see if I can go to this. This one is also very insightful. I will rewatch all of this, by the way, but let's do this so we can. Is that it?
In the late 1970s, Kunihiko Fukushima sketches out an algorithm. It's a solution to a computing problem that, in some ways, won't become practically relevant for another 40 years. But Fukushima knows he's onto something. When computers catch up, the schematics on his desk will help move artificial intelligence from the domain of fantasy to reality. After years of studying the human visual cortex, Fukushima has created a way for machines to do what we do best: to see the world, recognize patterns, and learn. Japanese-born Fukushima began his engineering career at 10 years old, leaving the island of Taiwan for Japan when the island fell out of Japanese control after World War II.
We are not allowed to bring anything except one baggage for each person. So because I didn't have anything with me, I didn't have any toy. So my uncle gave me transformer and electric motor, which he was trying to make when he was young.
Fukushima taught himself the fundamentals of electrical engineering in old textbooks, finished the electric motor, and by junior high school was building radios in his home. In a sense, from then on, Fukushima was always thinking about the future of visual and auditory technology. For instance, he'd earned his Ph.D. from Kyoto University after devising a method for broadcasting 3D television signals. This was in 1966. But it wasn't until he joined NHK, the Japan Broadcasting Corporation, that Fukushima stopped asking how machines could transmit audiovisual signals, wondering instead whether computers could receive them and, more importantly, make sense of what they heard and saw. Fukushima wanted to make a computer that worked like the human brain.
Recognizing images and patterns comes so easily to us that we rarely stop to think about how complex it is. Take the letter A, for example. It looks something like this, right? Or does it look like this? Or this? How about this? Your brain recognizes the letter A consistently, even though chances are you're looking at versions you've never encountered before. Fukushima understood that a pattern-recognizing machine would have to work like the brain. It would have to learn the concept of a given image, like the version of letter A you imagined a moment ago, and compare this conceptual understanding to real-world observations.
At first, we didn't know anything about neurophysiology or psychology. So we called some professors of neurophysiology to our lab, and they gave me a lecture for about 1 or 2 years.
Fukushima learned all he could about the brain's visual cortex, where cells were arranged into a neural network, a kind of circuitry completely different from the electronics Fukushima found familiar. But he soon realized this new kind of wiring was perfect for pattern recognition. Fukushima sketched up a network of electronic cells arranged in layers. A camera would feed an image into the cells. Layer by layer, the cells would analyze curvature and angles, the size and position of the lines, all the while comparing it to a single memorized concept of the target. In 1979, Fukushima called his revolutionary new machine the Neo-Cognitron. And with the help of NHK, he produced this quintessentially 1980s film showing off its pattern-recognizing capabilities. After his initial discovery, Fukushima and others spent years improving the Neo-Cognitron, giving it the ability to recognize sounds, videos, and even obstructed imagery, sometimes more capably than the human brain. Recognize any of these letters? Believe it or not, it's not a problem for newer versions of the Neo-Cognitron. As modern computers became smaller and faster, Fukushima's discovery became a core feature of modern artificial intelligence systems. Today, neocognitron technology gives industrial robots visual abilities, braking and steering systems for self-driving cars. It can identify cancer under a microscope as reliably as a trained specialist, and even recognize patterns in nature that point to coming natural disasters. Fukushima's 1979 neocognitron, decades ahead of its time, is just now entering its prime. As time goes on, artificial intelligence systems continue to redefine the role machines play in our daily lives. The neocognitron and its inventor will continue to hold a place in our cars, our pockets, and everywhere the great discovery story of humankind is told.
Okay, pretty cool. Right, so hopefully you've got quite a bit from this lecture. It's very important for you not to only learn how things work, how to work things, meaning how to work them yourself, how to apply them yourself, but also the story around it. Believe it or not, the story of invention is part of the education, because the narrative is going to hopefully imprint in you the journey of very game-changing innovation takes place. So hopefully the story of your own, integrated innovation will have semblance to that and echoes to that. So learning how technology gets here is not just for history nerds, okay? It's actually to inform you of your own journey. So hopefully you gain a lot from that lecture today. And with that, I think we end on a pretty good time. I'll see you guys in 2 weeks. Okay, Cap? And make sure respond to the Marco's invitation on the OpenAI. It's a rich resource. Thank you. You Cap? Ready, look. Ready.